Okay, I'd like to do the force between two current carrying wires. The two current carrying wires will put a force on each other. But before I do that, I'd like to go back to this problem. So we were trying to find the magnetic field, a distance b up the y-axis. And we had reasoned that the magnetic field due to this guy has to be that way, and the magnetic field due to this guy has to be that way, and that's a right angle. And so I'd like to just complete this problem and show you how you find the total magnetic field from this then. Looks like the total magnetic field, if we look at the x component of this vector, that's going to cancel with this one. So all I have to worry about is this y component, and I have two y components. Okay, so let's call this angle theta. And I'd like you to see that whatever this angle is, see this angle right here? This is, that angle plus theta have to be 90. So I'm going to call this beta. Okay, so beta plus theta is equal to 90 degrees. But come down here and look at this angle right here. I wish I could zoom in again, but this angle right here to this vertical, to the y-axis, that's a right angle too. And so I can say beta plus, let's call this alpha. Beta plus alpha have to also equal 90 degrees. So do you see how theta has to equal alpha? If beta is 60 degrees, that's going to be 30 degrees. And if that's 60 degrees, that's again have to be 30 degrees. So alpha, this angle right here, is equal to theta. Okay, well, there's a bunch of other ways you can get to that argument, but that's one of them. And so this right here, or I'll use this one. That's going to be b1 times the sine of theta. If that's theta, this is going to be b1 times the sine of theta. Okay, so b1 times the sine of theta is going to be, what I'm going to do is sine of theta is the opposite side over the hypotenuse. But this is also theta right here, apparently. And so that would be opposite A over the hypotenuse. And so b1, if you want to know just the y component of b1, it's going to be equal to b1 times the sine of theta. Now what I'm going to do is, for sine of theta, I'm going to do opposite over hypotenuse. So that's going to be opposite over hypotenuse. Now the hypotenuse of this is a squared plus b squared square rooted. Okay, but the total b then, write it a little bigger, is twice this. So it's going to be 2 times mu naught times I times a all over 2 pi, and then you can put those together. When you put those together, you are going to get, that's going to just give you a squared plus b squared. Okay, so that's the total field that's due to both of those. Okay, I don't know how clear that was, but good luck with that one. Okay, the force between two current carrying wires now. Let me just tell you that when two wires are positioned near one another, and if they have currents in them, they can put a force on each other. So let's have the wire be like this, and another wire be like this. Let's call this I1 and this I2. Okay, now let's just see what force I2 is going to have on it. Okay, the force that I2 is going to have on it is just going to be the force on I2, on wire 2, is going to equal I. Well, let's just see why there's a force first. There's a force because this is creating a field in this region. The field is going to be out of the page. See how I put my thumb down, and it's going to be the hands are going to be coming, the fingers are going to be coming out, and so there's dots here. There's a bunch of dots here. Now they get less as you go out. They're really a lot here, and of course there's X's over here from this. Yeah, there's our dots coming out and X's going in. Now this is interacting with this field by Philb, so it's going to be the force onto will be I2 times L cross B. Now this B is from wire 1. Okay, first of all, can we get rid of the cross product? Well, I would argue that L is this way and B is out of the page. So do you see how if this one is, if the L is that way and B is that way, those are at right angles. So the cross product then just turns into L times B, because you're supposed to take the part of L that's perpendicular to B. Well, all of it is. And then B is going to be the magnetic field due to I1, which is mu naught I1 all over 2 pi r. Let's say these are distance r apart. So 2 pi r. Okay, that is the force on 2. Sometimes they bring the L on the other side. So the force on 2 divided by the length, so now this is a force per length, is equal to mu naught times I1 times I2 all over 2 pi r. Notice that if I double my r, if I double the distance between them, the force actually goes down into half. This is not an inverse square law. Okay, so that's how that works. So the force on it is just going to be mu naught I1 I2 divided by 2 pi r. All right, I'm just going to do one other thing then. I want you to see that this works for wires, but it also works for charges that are moving by one another. So let's say there's a charge here, Q moving at a speed v. And then here's another charge, Q2 or Q prime, moving in that direction. Let's say they're both positive. Which way will Q prime be pushed? Okay, well, let's see. The magnetic field from this guy is going to be into the page. So this is making X's here. This guy is making X's here and dots here. It's a ring that goes around like this. Okay, this is going to interact with this one's field. So the force on Q prime, should equal Q prime plus V, I'll call this V prime, or times rather, Q prime times V prime, and then cross that into the magnetic field strength, QV cross B, and the magnetic field strength is going to be from this guy. So we're going to get that from this equation, mu naught over 4 pi times Q times V, not prime or prime, these are just Q and V, times the sine of theta all over this distance squared. Okay, now I'd like to convince you of a couple things. This is the magnetic field. Isn't the V perpendicular to the B? See how the V is perpendicular to the B? So I can get rid of that cross product. And then that sine of theta is, how is V and R related? It looks like V and R, this is theta. Looks like theta is 90 degrees. And so these both are going to simplify to this. The force on Q prime is going to be equal to Q prime V prime times mu naught all over 4 pi Q times V all over R squared. Okay, same kind of idea as the two wires. All right, thanks. I'll talk to you.